Our next talk is by Shasha from University of California, Riverside. She's going to talk about stealthy adversarial perturbations against real-time video classification systems.
Thanks for the introduction. So our work is stealthy adversarial perturbations against real-time video classification systems. This is a joint work. I'm Shasha, and I have collaborators from my university, UC Riverside, and Dr. Swami from US Army Research Lab. So adversarial perturbation is a hot topic. People find that deep neural networks are not robust to carefully design small perturbations. For example, the attackers could carefully design a perturbation based on this school bus image, and adding this perturbation onto the image, although the perturbation is very small for human vision system, DNNs would make mistake and misclassify it as an ostrich, or things that looks very different. So right now, most of the adversarial perturbation works are in image area. We are interested in if we could mess up with temporal information and attack a video system. So for video inputs, it has both static appearance information, which is same as images, but also dynamic temporal information. Here we showcase two datasets. Can you help to play the video? So this UCF11 dataset, it has diverse human actions. For this gesture dataset, can you help to play the video? So it had several gesture actions. So in this dataset, the actions are not very distinguished from each other in terms of appearance information, but more distinguished from each other in terms of temporal information. So in our work, we use UCF11 to investigate if we could carry on attack on coarse-grained actions, and we use gesture to represent fine-grained actions. So DNN-based video classification systems are more and more deployed, even in some security severe applications like self-driving cars, surveillance systems. So our paper aims to attack this kind of real-time video classification systems. So we assume white box attack, which means we assume we know the DNN model and we know the parameter value of the model. We also assume the attacker is capable to inject perturbations onto the real-time video stream. This has been shown possible by previous works. And last, we presume stealthy. Stealthy not only in the sense that this perturbation should be small enough for human vision system, but also in the sense that we want only the target action misclassified. The reason is that if too many mistakes happen, human may notice the malfunction of the system, and they may decide not to use the system. So now let's take a close look on how video classification systems work. They typically contain a sliding window and a classifier. So the sliding window extracts video clips from the video stream. The length of the sliding window determines how many frames in one input clip. And the stride of the sliding window determines the overlap between the input clips. Then the classifier would take the input clip and output the score for each class. If we plot the score for each action during time, we could get curves like shown here. So the peaks here in the curve means this kind of action, the corresponding action, may happening during that time period. So let's formulate our problem. We denote input clip as x and the score vector as q of x, and we denote the score for the ith class as q underline of x. Our attack goal is to find a perturbation. We use p to denote the perturbation. So our attack goal is to find a perturbation so that the DNN would output low score for the ground truth class. Notice here, the input is a clip, so the perturbation should also be a clip. If we use cross entropy loss, we would formulate our problem like shown here. So using this vanilla method gives us an immediate problem. So remember, we are doing a real-time attack, which means we need to generate perturbations on the fly with the same frame rate. This is computational intensive. So our solution is to use universal perturbations. Universal perturbations are universal in the sense that they work on any unseen inputs, as long as the inputs is from the same distribution as that of the training data. This way, we could generate universal perturbations offline, and the only online computation is to add the perturbation onto the video. To realize this, instead of minimize the cross entropy loss over one video clip, we minimize the sum of the cross entropy loss over all the training data. And here we use a generative model. We use this g of z to represent the function of our generator. Here we show the framework of our system. So we have some real-world video streams, and we sample from them, get clean video clips. At the same time, we have a generator. It tries to learn the mapping from the latent space to the perturbation space. Therefore, when we get a sample from the latent space and input it into the generator, we expect the generator to output a valid perturbation. Adding the perturbation to any input clip, we would expect the classifier to misclassify the inputs. So this post-process unit is, we will describe it later, is used for other challenges. So this generator and the post-process unit in total is our innovation. So now we have universal perturbations. They will make any input clips misclassified. However, this is not what we want. We want stealthy. So we propose dual-purpose universal perturbation. Dual-purpose universal perturbation only make the target action misclassified. To realize this, we have two parts in our objective function. So the first part, for input clips of target class, we want the DNNs to output low score for the ground truth class. And the second part, for input clips of non-target classes, we want the DNN to output high score for the ground truth class. Okay, until now, we have a stealthy universal perturbation. We are still one more step towards adding the perturbation onto the video stream. The story is that although we assume a white box attack, we know the length of the video clip. The clip boundaries are still non-deterministic. It is decided online by the sliding window. Blindly add the perturbation clip onto the video stream, there could be misalignment between the perturbation added by the attacker and the actually applied perturbations on the input clip. So we showcase two examples here. In the first figure, the upper part is the attacker's view, the lower part is the sliding window's view. Here, the attacker assumes a different starting frame as the sliding window. We can see here the extracted perturbation P1 prime is actually a combined version of two broken parts from previous intended perturbation P1 and P2. Also, in the second scenario, here the stride of the sliding window is half the length of the sliding window. The perturbation applied on the second input clip is also a combination of two broken parts. So if we assume there are 3 frames in one video clip and denote them as A, B, C, we can see here all the possible extracted perturbation clip could be ABC, BCA, and CAB. So how well could these perturbations work? We conduct an empirical experiment. Here, the abscissa is the offset between the intended perturbation and the extracted perturbation. As you can see, the attack success rate first drops, and then it becomes better. So it becomes better because then the extracted perturbation has a better overlap with the next intended perturbation, as shown in the lower part. So from this figure, we see that if misalignment happens, perturbations are broken and the performance would drop. So to overcome this problem, we propose circular dub. C-dub is a kind of perturbation whose circular shifted version is also a valid perturbation. The motivation here is that we found all the possible extracted perturbation are actually the circular shifted version of the original perturbation. As you can see here, this BCA is a circular shifted version of ABC. This CAB is also a circular shifted version of ABC. Therefore, this C-dub is designed to work even if misalignment happens and perturbations are broken. To realize this C-dub, we add a pro-process unit. This unit rolls the generated perturbation by a random offset before adding it onto the video clip. An even more crazy idea is to use a single frame perturbation. So this is actually a special case of C-dub. We realize this by using a 2D generator, which generates a single frame perturbation, and a post-process unit, which repeat this single frame perturbation and add it onto a video clip. So this 2D dub is good in the sense that they are lightweight and thus easy to store and use. However, they may have limitations in perturbing the temporal information, in the sense that the perturbation added on each frame are actually the same. Now let's see some experimental results. So we use the metric attack success rate in our testing, which for samples of the target class is a misclassification rate, and for samples of non-target classes is the correct classification rate. We first compare universal perturbation with dual-purpose universal perturbation. This table shows the result on UCF11 dataset. We see both perturbations performs well on target class. However, this universal perturbation has a low attack success rate on non-target class, which means it's not stealthy. So we talk about stealthy in details in our paper. If you are interested, please refer to our paper. So here we could conclude that this dub performs better than up in the sense that it guarantees this target action misclassified, and also the attack is stealthy. Next, let's compare dub with C-dub. We test them on both datasets. The abscissa here is the offset of misalignment. The first figure shows the attack success rate for the target class, and the second shows the attack success rate for the non-target classes. We observe here this C-dub guarantees a high attack success rate in both cases, no matter what the offset is. On gesture dataset, C-dub also performs better than dub in the sense that it guarantees high attack success rate for the target class, even when misalignment happens. Okay, last, let's compare C-dub and 2D dub. Here we have two test cases for gesture dataset. The first test case, we use sliding hands right as our target action. This action has a temporally similar action in the dataset, that is sliding 2 fingers right. And in the second scenario, we use shaking hand as our target action. This action has no temporally similar actions. Here we see the result. On UCF11 dataset, they perform similar, I would say. On gesture dataset, this 2D dub is not as good as C-dub, but pretty much similar. However, in the last test case, 2D dub is not as good as C-dub. To explain the result, so in the first two scenarios, there's no need to perturb too much temporal information. However, in the last test case, since there are no temporally similar actions, this 2D dub has difficulties to do the attack. Okay, to conclude our work, we identified 3 key challenges, And we use a generative model and succeed in generating very potent adversarial perturbations. We also outline some defense methods in our paper. If you are interested, please refer to the paper. Okay, that's all. I'm happy to take questions.
Thank you. So Ahmed Salim from CISPA. I have just a quick question. So why do you need the generator? So I didn't see any like feedback to the generator. So why don't you just create a static noise which you always add to the frames?
Yeah, that's a valid question. So we use the generator because we may not want only one perturbation. We want to explore the perturbation space. There could be many valid perturbations to attack one action.
Bimal Vishwanath, Virginia Tech. Great talk, enjoyed it. I have a quick question about, so you didn't show any samples of the videos that were perturbed. So my question is, my understanding is that universal perturbations are more obvious to the human observer. So was that the case? And when you applied your technique to, I think, make it stealthy, I think your definition of stealthy is slightly different. Did it become less obvious? Would it become less obvious to a human that this attack is happening?
Yeah, I agree with what you said. Of course, the universal perturbation is more obvious than perturbation specific to an input clip. But there are some previous research works, they define a quasi-imperceptible. So quasi-imperceptible is defined as 10 units out of the 255 unit. So we constrain our perturbation not bigger than 10 units in our paper. So we assume it's quasi-imperceptible.
Okay, just a quick follow-up is, say if you used an MSSIM score to look at different frames, would you see a big difference when you apply the attack and when there is no attack? As a defense, I was just thinking.
Yeah, that could be a defense.
All right, thanks.
Yeah, thank you.
More questions? I'll ask one. Could you comment on the various defenses that you discuss in the paper? And are they fundamentally different than sort of breaking this overfitting problem?
It's not actually based on only the model level. It's actually consider the consistency between actions. For example, if you have actions running and then kicking a ball, they are common to show up together. But if you have action running and then apply eye makeup, it's kind of strange, right? It may trigger some alarm.
And have you implemented any of those defenses?
Yeah, that's our future work. Yeah.
Hi, one last question. Georgia Saverio, Northeastern University. How much of the percentage of the video is actually perturbed during your experiment? Do you perturb the whole video or just a fraction of it?
Sorry, you asked how many percentage of the videos are perturbed?
Yes. Yes.
So here we assume we get a video stream, and on every frame we add the perturbation. So basically, all the frames are perturbed. Yeah, thank you.